Hi, my name is Vicky, and this is my constant velocity lab report. So the objectives of this lab are to observe an object at constant velocity, and this means that the net force is equal to 0. So we're going to use Newton's second law to model it on VPython. We're going to start with the momentum principle, which is the change in momentum is equal to net force times the change in time. And we manipulate this equation to get final velocity is equal to initial velocity plus F net over the mass times delta t. And remember, the net force is going to be equal to 0, so in this lab, final velocity is equal to initial velocity. So my observations, I took a video and put it through Tracker and extracted that data, and I also did the same on my VPython model, and I did a graph comparison. So this is my video of a ball rolling on a table at constant velocity. And I made a VPython model. So my initial position vector is 0, and my initial velocity is 0.4 meters per second. I determined this from my Tracker data. And I set my time to 1.4 seconds, which is the same as my video. And I used Newton's second law to predict the ball's motion and position. I'm going to run this. So I put these two on a graph, on a position versus time graph, and my Tracker data is it falls a little bit more short of the VPython model. And this could be for many reasons of forces unknown, the spin of the ball, but it's not exact. So what if my axes were changed? If I flip my axes, the magnitude of velocity would not change, but the sign would. And what does this mean? Is it possible for you to say how many pushes and pulls are added together to give 0 net force in the case that you observed? And no, it's not possible because there are too many variables to determine this, as seen in my video. Possible forces such as air resistance, friction, and gravitational force are not being considered. So, in conclusion, we demonstrated how velocity is constant when F net is equal to 0 using Newton's second law. Thank you so much.